Thermodynamics is the branch of physics that deals with the concept of heat and temperature and the interconversion of heat and other forms of energy. Interconversion of heat and other forms of energy means heat energy to mechanical energy. That is the job of heat engines. Similarly, using mechanical energy, heat energy is pumped from a region of lower temperature to a region of higher temperature, and this is a refrigerator. Conversion of electrical energy into heat, boiler. So in all these places, they extensively use thermodynamics. Important terms in thermodynamics. So we often use these terms to understand thermodynamics, to explain thermodynamics. Okay. System. It is the specified portion of the universe which is under thermodynamic study and is separated by the rest of the universe with a definite boundary. This is a container with some gas. So we are interested to see changes in temperature, pressure of this gas. Means this gas is the system and the gas is separated by the surroundings by well-defined boundary. The boundary can be real or imaginary. Okay. Now this is a system. This is the surroundings. Excluding the system, each and every other thing becomes surroundings. Now, let me draw one more. If it is single line, then the boundary is a conducting boundary. If I draw one more like this, then insulating boundary. This gas is separated from the surroundings through this boundary. And this is an insulating boundary. That is why it is mentioned with two lines. Surroundings. It is the portion of the universe excluding the system and capable of exchanging matter and energy with the system. So excluding the system, each and every other thing becomes surroundings. Boundary. The real or imaginary surface that separates the system from the surroundings is called the boundary. Metal container. So this is a real boundary. There is a gas inside this container and this is the surroundings. System, surroundings, and this is the boundary. Now, this room has air. I am interested to see changes in this part of air. So when I say in this part of air, you have to imagine a boundary. And this is imaginary boundary. So molecules are going from this region to this region, they are entering into this region. So all these things are happening. And in my explanation, I have to imagine this boundary. That is imaginary boundary. Open system. Container with some liquid. And this liquid is heated. When liquid is heated, then liquid goes to vapor state. See, molecules of the liquid are in vapor state. So there is exchange of matter between system and the surroundings. And there is also exchange of heat energy between system and the surroundings. Because if we touch this container, we can feel the heating effect. Means there is leakage of heat energy from the system into the surroundings. So this is an example for open system. Closed system. It is a system in which it can exchange energy but not the matter with the surroundings. This is a container with liquid. This liquid is heated. There is exchange of energy between surroundings and the liquid. But there is no exchange of matter between liquid and the surroundings. So such type of systems are called closed systems. No exchange of matter. closed system. And closed systems are represented by single wall boundary. Single wall boundary means conducting wall. That conducting wall ensures that there is exchange of heat energy. Isolated system. It is a system in which it cannot exchange both energy and matter. Both energy and matter with the surroundings. If this is the system, gas or liquid, something which is under observation, then this gas should be suitably insulated. Double line means insulating walls. Now, there is no exchange of heat energy between gas and the surroundings. Also, there is no exchange of matter. So, such systems are called isolated systems. Isolated means completely isolated in terms of energy and matter. Thermodynamic state. A thermodynamic state is specified by 5 state variables: pressure, volume, temperature, internal energy, and entropy. In the case of coordinate geometry, we use x, y, and z. They are the variables. But in thermodynamics, to specify condition of a system, we can use these as the coordinates: pressure, volume, temperature, internal energy, and entropy. That is why they are called thermodynamic variables. And a state can be represented by thermodynamic variables. Adiabatic wall. It is an insulating wall, can be movable, that does not allow flow of heat, flow of energy from one to another. Adiabatic wall is represented by this. If there is this gas isolated from the adiabatic walls, means there is no question of exchange of energy and matter between system and the surroundings. Now, this is a cylinder. This cylinder is fitted with a piston like this. So, this is the piston. This shaded portion is the piston. This is the movable part. The piston is also represented by 2 walls, adiabatic walls. Adiabatic wall, adiabatic walls. And if there is a gas, then we can decrease volume of the gas by moving this piston inward, or we can observe expansion by moving this piston outward. So there is a piston which is insulating, and this is a movable part in this system. So adiabatic wall can be rigid fixed or movable. Diathermic wall. It is a conducting wall that allows energy flow from one to another. This is diathermic wall, conducting wall. There is gas. If the gas is heated, then gas absorbs heat energy, and from the gas there is exchange of energy between gas and the surroundings, system and the surroundings. Now, single line, diathermic wall. Double line, adiabatic wall, adiabatic walls. Single line. This is system A and this is system B. System A is at say 50 degrees Celsius and system B is at 20 degrees Celsius. These two systems are separated by this wall, single wall, diathermic wall. So there is exchange of energy between A and B because of this diathermic wall. There is no exchange of energy or matter between A and the surroundings, B and the surroundings. And there is no exchange of matter between any two systems. This separates these two, so there is no exchange of matter. So this is how we can make use of diathermic wall and adiabatic wall. Remember, we are just concentrating on different terms used and what is the actual meaning of those terms. Okay. Internal energy. Internal energy is the sum of the kinetic energies and potential energies of the molecules. Sum of kinetic and potential energies. So time being, this is a system with gas. Here, gas molecules are moving randomly means they have kinetic energy. This molecule has kinetic energy. Similarly, because of some reason, these gas molecules can have hidden energy, potential energy. Don't worry about the reason behind potential energy at this stage. Okay, there is some hidden energy, that is potential energy. Gas molecule is moving, that is kinetic energy. Sum of these two energies is the total energy, nothing but internal energy of the system. So internal energy includes both kinetic as well as potential. Heat capacity. Heat capacity of a substance is the quantity of heat required to raise the temperature by 1 Kelvin. This is water at 50 degrees Celsius. Equal amount of water at 90 degrees Celsius. Okay. If a body is in contact with this 50 degree water, then this water can supply some amount of heat energy. If the same body is in contact with 90 degree water, then this can supply more heat energy because heat content is less, heat content is more. So that is why heat capacity is always defined per degree change in temperature, per degree Celsius change or per Kelvin change in temperature. Heat capacity, denoted by capital S, is the heat supplied to rise in temperature, heat per Kelvin, equal to, equation is delta Q by delta T, and SI unit is joule per Kelvin, joule per Kelvin. Specific heat capacity. Specific heat capacity means with respect to specific mass. Standard is 1 kg mass. Specific heat capacity is the quantity of heat supplied to raise the temperature of unit mass by 1 Kelvin. Heat capacity is heat required to raise the temperature by 1 Kelvin. If that heat energy is specific to mass, then it is called specific heat capacity. Specific heat capacity is 1 by mass into heat supplied by rise in temperature, equal to 1 by mass into delta Q by delta T. Consider a metal of mass 1 kg. Metal of mass 1 kg. This 1 kg is at 20 degrees Celsius. By heating this 1 kg mass, 1 kg metal, its temperature is increased to 21 degrees Celsius. For that, say 300 joule of energy is required. Let me repeat. To raise the temperature of 1 kg metal from 20 degrees Celsius to 21 degrees Celsius, 300 joule is required. Now specific heat capacity of this metal is 300 joule per kg per Kelvin for 1 degree rise in temperature. So specific heat capacity is 300 joule per kg per Kelvin. So this is how specific heat capacity can be used. Therefore SI unit of this is, SI unit of specific heat is 1 by mass joule Kelvin, joule per kg per Kelvin. Small letter k, capital letter K. Molar specific heat capacity denoted by C. Now the heat capacity is specific to number of moles. That is called molar specific heat capacity. Is the quantity of heat supplied to raise the temperature of 1 mole of a substance by 1 Kelvin. So specific heat capacity, molar specific heat capacity is 1 by mole heat supplied by raising temperature. 1 by mu into delta T by delta Q by delta T. The difference is only with this number of moles. 1 by number of moles says per mole, per mole. So SI unit of this is joule per mole per Kelvin, joule per mole per Kelvin. Macroscopic variables in thermodynamics: temperature, pressure, volume, internal energy, entropy. These are called macroscopic variables because volume means thermodynamics is not interested into volume of a molecule. It is volume of gas which matters. Volume of gas means it is a bulk property. More number of gas molecules should be present. If more number of gas molecules are there, then the pressure can be well defined. There is no pressure defined for a molecule, but pressure is defined for a gas. Similarly, volume is with respect to number of molecules, not volume of a single molecule. Temperature, temperature of an electron is not defined. Temperature of a molecule is not defined. This temperature is also a collective property. Temperature of gas means the gas molecules will be randomly moving, and that is the reason for temperature of the gas. If the gas molecules are moving with higher speed or speeds, then we can say that it is at higher temperature. If there is a metal, then atoms are vibrating, molecules are vibrating about their mean position, means that is the reason for temperature of the metal. So it is not temperature of a molecule, it is temperature of the material, temperature of group of molecules. That is why they are called macroscopic variables. Example for microscopic variable: diameter of a molecule, radius of a molecule. So thermodynamics doesn't deal with a molecule. Isotherm: pressure volume curve for a fixed temperature is called an isotherm. Y-axis pressure, x-axis volume. This is an isotherm. This is an isotherm. This curve is a pressure volume curve, or you can simply call it isotherm, provided the changes in pressure volume take place at constant temperature. If these changes are happening at temperature T1 and these changes are happening at temperature T2, then this is one isotherm, this is second isotherm. Iso, same, therm, temperature. Extensive variable: it is that thermodynamic variable which depends on size. Example is volume. Intensive variable: it is that thermodynamic variable which doesn't depend on size. Example, temperature, pressure. Let this be a container with some gas. Temperature of the gas be 30 degrees Celsius and volume is V. Okay. Now, let me consider small portion, this much. Volume of this portion is not equal to V. Means volume divides if I consider small portion or some portion. Whereas temperature of this portion of gas is again at 30 degrees Celsius. See, this 30 degrees Celsius temperature or temperature doesn't depend on size of the system, whereas volume depends on size. By splitting, volume changes, means it is an extensive variable. By splitting, temperature is not going to change, means temperature is an intensive variable. Similarly, pressure. If gas is at pressure P, then even this portion of gas will be at pressure P. Means by splitting, pressure remains same. So pressure is an example for intensive variable. Product of an intensive and extensive quantities is an extensive quantity. Pressure is an intensive quantity. Why it is called an intensive quantity? Because pressure doesn't depend on size. Volume is an extensive quantity, extensive variable. Volume depends on size. And product of these two gives work which is an extensive property. Suppose this is the container with gas at some volume V. Work done to expand this volume by small amount is 2 joule. Work done to expand this gas by large amount is 15 joule. See, work done depends on size. You consider this much portion. Work done to expand this much portion of gas is 1 joule. So, work done depends on size of the system, means it is an extensive variable. So, that is the meaning. Product of intensive and extensive is an extensive variable.